Peter? Peter? Do you guys have eyes on Peter? Peter! Peter! Oh, Peter, there you are. Your keynote is beginning. We gotta get you mic'd up and on stage. Can't miss your cue. We have a packed audience. We've already distributed all the t-shirts. We need to keep this keynote on time. Oh no, I just had a terrible thought. What if we run out of beer?
Last year, I specifically asked our marketing people not to schedule my rehearsal during the Seahawks game. Well, I guess the good news is my rehearsal didn't conflict with the game. Unfortunately, the game is during my keynote. Ah, karma. I've got an idea. What if we did this keynote my way?
Good evening, everyone. Cris Collinsworth here, joining you at reInvent to cover the action on stage during Monday Night Live with Peter DeSantis. So much excitement in Las Vegas right now. Can't wait to hear what AWS has in store for all of us. Yeah, it was an incredible year for AWS, but you can tell they're still hungry and they're listening to those customers. And it's that kind of focus and dedication that results in unbeatable innovation. The investments AWS has made over the past 12 months in compute, networking, and hardware will be huge here this evening. And do not underestimate the lasting impact an acquisition of Annapurna had. Last year, Peter discussed how Nitro, delivered by the Annapurna team, was helping to accelerate AWS's development of custom hardware and instance types. Now let's check out how these investments have played out for AWS customers. Well, that signals the start of our keynote. Now let's go to the stage and join the action.
Please welcome Vice President of AWS Global Infrastructure and Customer Support, Peter DeSantis.
Good evening. Welcome to Monday Night Live. What an amazing band. Now, there's only one thing better than football on Monday night, and that's talking about infrastructure. And that's what we like to do here at Monday Night Live. And tonight, we're going to do it while we talk about some of the most amazing and demanding workloads out there. Last year, at Monday Night Live, we launched our first network-optimized instance. That first instance was the compute-optimized family, the C5N. Now, these instances were the first cloud instances to provide 100 gigabit instance networking with low latency and scalable throughput with all the elasticity and features of AWS. Now, this is a big deal. These are high-performance instances with an ultra-high performance network with all the elasticity and all the functionality of EC2. You can launch one instance, you can launch 1,000 instances. You can do it when you want. You don't have to call us to set up a static cluster. You spin them up when you want them, and you shut them down when you no longer need them. And last year, I mentioned how excited I was that these innovations helped us achieve something that we had been working on for almost a decade. The ability to allow high-performance computing applications to run on AWS the same as any other workload. And I'm delighted to report that over the last year, we've seen this goal become a reality. So I want to share some of that progress with you tonight. But first, I want to give you a little deeper look into some of the innovations that are underpinning what's making this possible. Now, I know some of you are thinking, wait, do I care about HPC? Well, I hope so, because HPC impacts literally every aspect of all of our lives. HPC is used to solve problems in science and engineering. These are big, hard problems in science and engineering. For example, HPC is used to create safer, more fuel-efficient cars and airplanes. And increasingly, HPC is being used to find new treatments for disease. And HPC also underpins the critical weather forecasting systems that are used to predict the paths of hurricanes and figure out how winds are going to spread wildfires. And these predictions are used to save lives. So HPC is really important. So what is an HPC workload? While there's no precise definition of an HPC workload, the one near constant is the workload is too big, and usually way too big, to fit on a single server. This is what makes them exciting from an infrastructure perspective. And what really differentiates HPC workloads is the need for high-performance networking so that those servers can work together to solve a problem. Typically, each server works on a portion of the problem, and then all the servers share the results with each other. And this information exchange allows the servers to continue doing their work. The need for tight coordination puts significant demands on the network, because while this coordination is happening, useful work is usually not. And this problem only gets worse as you distribute the work to more servers. So the larger you make the cluster, the more demands there is on the network. So to scale HPC workloads effectively, you need a high throughput, low latency network. And the better the network performs, the bigger you can scale your cluster. And that means you get faster results. So to solve the hardest HPC problems, we use supercomputers. And if you look really closely at a modern supercomputer, it's really just a bunch of servers and a purpose-built dedicated network. The servers have all sorts of processing capabilities. They can be built with regular processors or specialized processors, GPUs or FPGAs. They can have a lot of memory or they can have a little memory. It just depends on the workload. Today's largest supercomputers often contain thousands or sometimes tens of thousands of servers. And the networking in a supercomputer is typically a proprietary networking stack, which is optimized to provide great performance in the limited confines of the supercomputing cluster. And the network also provides specialized functionality to help the HPC applications get the best performance from the network. Now, the other thing about supercomputers is they're custom built. And this means they're really expensive, and they take months, if not years, to build. The cost for these systems can easily run into the tens of millions. And the largest supercomputers, the ones that are used for things like weather forecasting, those can cost hundreds of millions of dollars. Now, there aren't too many upsides to high cost and long lead times. But it does mean you have plenty of time to pick a cool name and an awesome paint job. Seriously, supercomputers all have the coolest paint jobs. But of course, there are also some downsides. The main problem is getting access to a supercomputer. Because of their high cost, access is tightly regulated. Usually, only the highest value applications have access to the supercomputer. The goal is to keep them very highly utilized. Think of how frustrating it must be if you're an engineer or a scientist waiting to get access to one of these supercomputers. Would you hire 100 software engineers and give them 10 servers to write their code on? No. With more access to low-cost supercomputing, we could have safer cars, and we could have more efficient airplanes. We could have more accurate storm forecasts. We can have better treatment for diseases. And we can unleash innovation by giving everybody the ability to run even the most demanding workloads, not just the people lucky enough to work at the largest companies or national labs. The other big disadvantage of supercomputers is when you spend hundreds of millions of dollars on something, you tend to keep it around for a while. And so while they perform great when you first get them, they can be slow after a couple of years. And this means that HPC applications often have old hardware. So, if we want to reinvent high-performance computing infrastructure, we have to reinvent the supercomputer. So how do we go about reinventing the supercomputer? By enabling HPC applications to run as easily as any other application on AWS. And how do we enable HPC applications to run on AWS? Well, we've been working on that for several years. And as you've probably guessed, it all starts with the network. A few years ago at this keynote, James Hamilton discussed an exciting trend in data center network. And I see him out there in the audience, so I better get this right. Much like servers had done previously, networking equipment was undergoing a significant transformation from vertically integrated big box networking gear to a world of diverse vendors innovating on all the key components, like the network switching chips or the optical switching technology, which accounts for the vast majority of the cost in a data center network. So we've made big investments in building our own switches and working closely with our suppliers to innovate on those key components. We've also built our own networking software to run on these switches. Having complete control of the hardware and software in our network has allowed us to lower cost while improving security, reliability, and operational performance. And having end-to-end control of the network has allowed us to innovate faster. James predicted that this change would drive the cost of networking down and lead to a significant increase in the amount of networking available on servers. We're now 3 generations into this journey, so let's see if he was correct. One way to look at this is to compare the networking and CPU of our compute optimized family, which we call the C family. Now, the C3 instance was built with the first generation of the new network, and this was the one that was made available when James talked about this transformation. The C5N instance is the one we launched last year and has really become available this year. Using common CPU benchmarks to approximate the computing power on these servers, the C5 instance provides 10 times the networking capabilities, but only about 3 times the compute capabilities. So that means it provides 3 times more networking for the same amount of compute. Now, whether you look at integer performance or floating point performance, and these are just benchmarks, networking performance has indeed been outpacing improvements in CPU. And there's no doubt that we're seeing the improvements that James predicted. But this is not enough. To run HPC applications, you need a ton of aggregate bandwidth in your network, because all of those servers need to be able to talk to each other. So let's look at that. What you see here is a logical representation of our data center network. We call this portion of our data center network a placement group network. An availability zone can have lots of placement group networks connected by higher portions of the network. But to create a high throughput, low latency computing cluster like you need for high performance computing, you need to launch your instances inside of the same placement group network. And conveniently, EC2 has an API for that. Now, over the last several years, we've made investments in our network, and we've been able to increase the capacity of our data center networks while simultaneously decreasing latency. Also very important. So let's look at that. This is our first generation of this network, the one that we delivered the C3 instance on in 2013. It had 460 terabits of networking capacity. Now, that's large enough to connect about 4,600 100 gigabit servers. And the one-way latency through this network was about 12 microseconds. Our third and latest generation placement group network provides 10 petabits of networking aggregate capacity. That's 10,000 terabits, or 20x what our first generation placement group network provided. Now, that's enough capacity to connect 100,000 100 gig servers. And the one-way latency through this network is 7 microseconds. So let's say that you want to launch a cluster of 5,000 C5N instances, the ones with the 100 gig network interfaces. That cluster will have 360,000 cores and almost a petabyte of system memory. That's a really big supercomputer. And that cluster wouldn't have fit in our first generation network at all. It was just too big. But it only requires 5% of our latest generation placement group network. Now, this is really exciting, because one of the benefits of cloud computing is elasticity. And the way you get elasticity is by being a relatively small fish in a big pond. And we fully expect this trend's going to continue. As we deliver future generations of our data center placement group network, supercomputers are becoming an ever increasingly tiny portion of the overall network. And this will lead to the elasticity that will allow us to realize the vision of launching even the largest supercomputers with the same elasticity as any other application. No more waiting for capacity, no more being stuck with old hardware. You can launch your supercomputer when you need it. Okay, so we've got our network, check. But a placement group network is not a dedicated network. It's a shared cloud network. So to make this network useful in a cloud computing environment, we need to do a whole bunch of work to virtualize the network. And this is the second place where HPC practitioners get skeptical. Sure, you have a great network, but I can't use it. I need a dedicated network. And this brings us to the second item on our to-do list. We need to move all the virtualization to AWS custom chips and hardware to minimize latency and maximize performance and scalability. And for that, we need the Nitro controller. Now, I gave a pretty deep overview of the Nitro controller last year, and you're going to hear a lot about it this week. This is actually a C5 server, and that highlighted section is the Nitro controller. The Nitro controller is specialized hardware that uses AWS-specific chips and is built into every EC2 server. One way to think about the Nitro controller is like a little separate computer that runs on every EC2 server and manages all the EC2 instances on that server. The Nitro controller does all the work to virtualize the network and the storage and the EC2 environment. This provides a number of benefits, including better performance, improved security, and unique instance capabilities. But tonight I want to focus on one of the benefits, and that's performance. Let's look at how the Nitro controller improves EC2 performance. Well, the first is the thing we just talked about. All the virtualization functionality of EC2 runs on the Nitro controller. So this means that all the main system resources are available to the user's workload. And that means there's no virtualization tax, none. No stolen CPU cycles, no sharing of critical caches, nothing. Your application runs directly on the server and has performance that's indistinguishable from bare metal. In fact, because the Nitro controller secures all the AWS network and hardware, you don't even need to run a hypervisor at all. You can run your application directly on the EC2 server, natively. The second benefit is because the Nitro controller is built using custom AWS chips, network traffic is virtualized with minimal latency. And because we're investing heavily in building new chips with Annapurna Labs, we're able to innovate to improve performance and reduce cost on this even further. Finally, because the Nitro controller is totally separate from the main server, it can be scaled independently. And this means that if you want more networking throughput, you can use the same server, but you can add a larger Nitro controller. This is exactly what we did with the C5N. If you see up here the C5 and the C5N, the only difference between these two servers is the C5N has an additional Nitro controller that's got 4 times the resources of the main Nitro controller. And that Nitro controller is entirely dedicated to the high-speed networking of the C5N. Okay, so we can check off the network, and we can check off the virtualization. But there's another objection that we hear from practitioners. I can't use a standard network. I need a network that supports optimized networking with kernel bypass. So, of course, we had to add that to our to-do list. Let's take a look. Most applications that you probably run use TCP. TCP is great. It makes communication easy. It handles things like reliability and packet ordering. But TCP is a general-purpose communication library, and it's not particularly well optimized for HPC applications. First, TCP runs in the kernel space of the operating system. And this makes it optimal for sharing a network connection amongst all the processes running on your box. But sharing requires overhead, and this introduces latency and variability. And this is too costly when microseconds matter and latency consistency is paramount. So, an additional problem with TCP is that it's designed to deal with the internet. And things on the internet happen in milliseconds. But within our data center, the packet delivery time is measured in microseconds. And as a result, TCP can introduce orders of magnitude latency variability. And this just won't work for high-performance computing workloads. Finally, TCP handles general networking conditions quite well, but it's not particularly well suited for the challenges that HPC applications introduce. One of these situations is a condition known as incast. And this is where a lot of servers are trying to send a lot of data to one single server, effectively overwhelming that single server. Incast can happen during that synchronization phase that I showed you earlier. The surge of traffic overloads the receiver, and this results in dropped packets and inefficiency. Let's look at a little experiment to demonstrate the problem. In our experiment, we're going to have 10 EC2 C5N instances, all trying to send 8 gigabytes of data as quickly as they can to a single EC2 instance. Now, all 10 of those instances on top have a 100 gig network connection. And the one server on the bottom also has a 100 gig network connection. So clearly the guy on the bottom is the bottleneck. Now, in a perfect world, each of the servers on the top would get about 10% of the capacity of the server on the bottom. And if that were true, the transfers would happen in about 6.4 seconds. And that's just the math for how long it takes to move 8 gigabytes of data over a 10 megabit network, or a 10 gigabit network connection. Let's see what really happens. These two graphs show two of the TCP senders, basically what they experienced. Now we're looking at the fastest sender, the one that got its 8 gigabyte data transferred the fastest, and the slowest sender. Now, the first thing you're going to notice about these graphs is TCP has a huge amount of variability. The throughput thrashes from near maximum to 0 and back again. And this is because TCP overreacts to packet loss, and it doesn't recover nearly fast enough to help us. So you can see our fastest sender completed its work in about 6.84 seconds. Now, this is slower than our 6.4 second optimal time, but it's not too bad. But the slowest sender took 8.32 seconds. That's over 20% longer than ideal. And this lack of consistency can greatly impact the performance of high-performance computing applications, because synchronization can't complete until all the data makes it through. And the bigger the cluster, the worse this problem gets. So how do we fix it? We launched EFA, or Elastic Fabric Adapter. Now, EFA is a networking stack that's designed for the most demanding applications. And it's optimized to take advantage of the AWS data center network and the Nitro controller. EFA starts with a communication library that you install in your instance. And this library enables your applications to send messages directly to the Nitro controller. So EFA completely bypasses your kernel and TCP and requires no resources from your instance. Instead, EFA hands those packets to the Nitro controller, and this is where the hard work is done. We implemented a transmission protocol on the Nitro controller called Scalable Reliable Datagram, or SRD. Now, this is a networking protocol that we designed internally using our deep knowledge of how our networks operate and how they perform operationally. And this deep knowledge allowed us to do things like take maximum advantage of all the excess throughput in the network. It also allows us to detect packet loss or delay in microseconds and retransmit packets, several orders of magnitude faster than TCP. And because all this is done on the Nitro controller, there's no resource consumption on the main server. The HPC applications there get to use all those resources for their running code, but they can still have a maximum network performance and scalability. And EFA is designed for these very demanding network applications. So of course, it deals with problems like incast. Let's look at that experiment one more time, this time using EFA. So on the left, I have the graphs we just looked at with TCP, where throughput was thrashing up and down and times took a while. On the right, we see the same experiment run with EFA. And again, I'm going to show you the slowest sender and the fastest sender. Now, what's remarkable here is that EFA senders get very consistent throughput throughout their run. Essentially, they're getting their fair share right from the start and through their whole data transfer. This is because SRD quickly detects the incast problem and adjusts in microseconds to give each stream a fair share. And with EFA, the fastest sender finishes its transfer in 6.36 seconds. That's basically optimal. And the slowest sender only takes 6.83 seconds. Now that's remarkable. The slowest EFA sender is actually faster than the fastest TCP sender. So this is the consistency and fairness you need to make HPC applications scale. Okay. So we've got a hardware-optimized kernel bypass networking stack. We must be pretty much done here. There's one more thing we need to work on, which is to make these EC2 easy to use. We need to make it easy for HPC practitioners to use the tools they know. So we've integrated EFA with all the most popular HPC communication libraries and applications. Practitioners can use all these tools on EC2 with minimal changes to their applications. Oh, all right. I think that pretty much does it. We have what we need to run the most demanding applications. And we started a year ago with that C5N instance, but we now have 8 network-optimized instances. We have the C5N, the P3DN, the G4DN, the M5N, the R5N, and the I3EN. That little N at the end is what you know, then you know it's network optimized. So now you can pick the right instance to match your workload. And we've also added services like Lustre FSX, which is a file system specifically designed for high-performance computing workloads. We expect our pace of innovation to continue to accelerate as customers bring us more and more demanding workloads. So hopefully, I've convinced you that we have what we need to reinvent the supercomputer. I feel like I'm forgetting something. We need great artwork. And of course, we have that too. There we go. All right, now let's get to the fun. Let's get to the fun part. Let's look at what customers are doing with this functionality. I started this evening talking about computational fluid dynamics. Now, this is a classic HPC workload, and it's used to do all sorts of things, not just design more efficient cars and planes. A great example of a customer doing CFD on AWS is Big Ass Fans. Big Ass Fans makes, well, big fans. These fans are used for all sorts of commercial and industrial applications. And they worked with one of our partners, CFD Direct, to create an app that they call Spec Lab. And this application lets potential customers quickly and easily create models of their buildings and then test various configurations of their fans in those buildings. Now, this allows customers to avoid costly mistakes before installing the fans. Before moving this application to AWS, Big Ass Fans could only do this work for a small handful of their customers, using a dedicated on-premises compute cluster. With the application running on AWS, they can now run simulations for hundreds of customers and for just a few dollars, so they can scale to meet their business. And best of all, each of the simulations only takes 30 minutes. It used to take over 6 hours with their on-premises cluster. Now, this is the result of being able to scale out to more instances and take advantage of the network that we just talked about. Now, CFD is great, but there's probably a few of you in this room that are familiar with HPC, and you're saying, CFD, it's not a real HPC workload. OK. So maybe we'll talk about the granddaddy, or more appropriately, the grandmother of them all, weather forecasting, predicting Mother Nature. Weather forecasting is actually one of the most demanding workloads, and it requires some of the biggest supercomputers. And we have been working with several customers over the last few years to run their weather forecasting on AWS. And we have heard every objection possible. You can't get the same latency in the cloud. You don't have my exotic CPUs. You don't have the networking technology that I need. Well, we're persistent, and we kept talking to these customers. And I'm excited to tell you that we're finally starting to see some amazing results with customers running weather forecasting on AWS. Let's have a look. The US Naval Research Laboratory recently presented the results of their work running their weather forecasting in the cloud. This graph summarizes the results. This first line that you see up here is the performance they get with their on-premises supercomputer. Now, this line exhibits everything you want from a supercomputer. You can see that it has consistent scaling. As you add more processors, you get more performance. This is what you want from a supercomputer. Now, the first thing they did was test our C4 instances. Now, this is our last generation instance. It has a 25 gig, not a 100 gig network, and it doesn't have EFA. And what you can see here is it scales fine to about 160 processors, and then you keep adding capacity after that, and you don't get much back. As the cluster gets bigger, performance gains diminish radically. And this is because of all the networking issues that we talked about earlier tonight. So let's look at what happens with C5N. This FIDO line shows their C5N using EFA doing the weather forecasting. Now you can see the C5N cluster scales in the same linear fashion as the on-premise supercomputer. You see an absolute performance advantage, and this results from the fact that they have access to the latest generation processors on EC2, and their supercomputer is several years old. This is one of the benefits we talked about. But the most exciting part of this graph is that they demonstrated they could scale with the same consistency as a traditional on-premise purpose-built supercomputer. There are not many HPC applications more demanding than weather forecasting. And we can now run these workloads on AWS. So this is super exciting. Now, this was just a few of the customers who are having success running HPC on AWS. Our investment in high-performance computing are helping customers go faster. And I'm not just talking about business speed. Sometimes I literally mean go faster. Here to share some of their journey with HPC on AWS is performance expert and technical consultant at Formula One, Rob Smedley.
Good evening. A light smattering of applause. Thanks for having me here tonight. It's a great honor and a great pleasure to come and talk to you about Formula One. Formula One is arguably the greatest racing spectacle on earth. There's hundreds of, well, there's a Formula One fan. I knew there was going to be one. 500 million fans who tune in to the event every single time we put on a race. It really is arguably the greatest racing spectacle. But we at Formula One, we have a mission. We want to make it more engaging, more intriguing, just a better overall product, something that entertains more. And there's a key strategic moment coming up for us, an opportunity in 2021, where we're going to make seismic shifts and changes in the technical regulations, in the sporting regulations, in the sport overall. And when we engaged our fan base and we asked them, what do you want? The biggest thing that everybody wants is more wheel-to-wheel racing. They want to see the cars, inches from each other and racing, like all of them great iconic moments that you've seen. And the enabler to do that, believe it or not, is aerodynamics. So let's talk about the aerodynamics, and I'm going to take you through that story. So the first part of it is aerodynamics. Why bother? What does it do? The teams work relentlessly to produce downforce. Downforce is what pushes the car into the ground. It's what creates grip. It's what makes the cars such a spectacle going around the corners at such high speed. And then you've got the other part of aerodynamics, which is drag. Drag is the part that slows the car down in a straight line. So as the car goes down the straight, being powered by 1,000 horsepower, the drag's trying to slow it down. So you want to maximize the downforce, but you want to minimize the drag. And if we look at the development rates in Formula One, of downforce in particular, it's huge, it's immense. So the curve that you can see behind me here is fairly representative of a downforce curve. And as the speed increases, the downforce goes up. And it's exactly the opposite of an aeroplane. So when you sit on the tarmac and you go down the runway, as you build up the speed, eventually the wings give the aircraft enough lift and it goes up in the air. Formula One car is exactly the opposite. As the speed goes up, it gets pushed further and further into the ground. And at a certain speed, as you can see here, at around about 100 miles an hour, this is just to give you an example of how much downforce these cars generate. At around about 100 miles an hour, it creates about 1,000 kilos of downforce, which is about the curb weight of the car. So that means that if we turned the racetrack upside down and ran it above 100 miles an hour, it would actually be able to run upside down and stick to the ceiling. So, how do we develop aerodynamics? There's two ways that we develop aerodynamics in Formula One. Large teams of engineers, they work in the wind tunnel and they work in CFD, computational fluid dynamics. The wind tunnel, it's a scale model, around about half the size of the car. It's a very, very accurate representation. We make changes to that scale model. We blow air over it inside the wind tunnel, and we check whether them changes are positive or not. Computational fluid dynamics, instead, is essentially a virtual car in a virtual airspace. And we've been using CFD now for about 20 years. And as we've got more and more sophisticated with CFD, it's given us more and more insight into the flow physics. And what you see behind me here is a really, really interesting slice of the rear axle of a Formula One car. Those two blue dots that you can see towards the center line, they're called the vortex structures. And vortex structures are the aerodynamicist's friend, because they're very, very high energy airflow that go under the diffuser, underneath the floor of the car, and they create suction and pull the car into the ground and create grip. The pink hue that you see around the outside of the car, that's called the aerodynamic wake. And what the aerodynamic wake does is when the free stream, when the air passes over the car, it gets very, very turbulent, it becomes non-laminar, and it creates this wake, which is bad for aerodynamics, wake bad, okay? And when we looked at how we were going to improve Formula One, it was this wake structure that we had to improve. And essentially, this gives us the development, the golden triangle in Formula One, where you go from CFD to wind tunnel, to the track, you test it, and then you go back again. And you keep going round and round this golden triangle. And CFD plays a huge part, plays a very, very key part in the development. And CFD has always been a supercomputer problem. It's always been a HPC problem. The architecture that you can see behind me here, believe it or not, is the first architecture that we used in Formula One. And what we did was we took 20 CAD terminals, and when the designers went home on a night, we used to daisy chain them all together. And we made our first supercomputer, a 20-core supercomputer. Believe it or not, that's exactly what we did. And we used to do the CFD runs. And when they came back in the morning, we'd disassemble them. Today, we use around about 200 cores within the teams, and it's about 2,500 times the computational power that you can see of that architecture there behind me. So let's frame the problem. The problem is this. The car behind, the red car, in our diagram here, when it's 1 second behind, it loses 30% of the downforce, a huge number, okay? When it's half a second behind, which is the speed that you need to close in and get this wheel-to-wheel racing that we're searching for, it's losing 40%. So we turn to Formula One, we turn to aerodynamics and to CFD in Formula One in order to try and solve this problem. And what we had to do is we had to build a two-car simulation. What you see behind me is the current generation of cars. And when you see the wake effect, when we go into the pressure domain and you see the wake effect of that car behind, you can see how powerful it is and how much it destroys the aerodynamics of the car behind. This is where we lose around about half of the downforce. So what we had to do is we had to set around designing a new generation of car in order to improve the wake effect. And what you see behind me here is the 2021 version. This is what's coming up, okay? And what you're going to get as this animation moves around is a driver's eye view. So right now, you can be sat behind that car, and you can see the wake effect. It's an upwashing wake, and it's going over the car. But we had to completely redesign the car to make that happen. It's a huge HPC problem, a massive HPC problem. And this is where the partnership between Formula One and AWS was so important. Two companies, their DNA in problem solving. Let's just try and frame for a second the size of the HPC problem we've got. If you take a single car CFD run, and you take the most powerful home computer on the market today, if you wanted to do one run with a single car, not the two cars that we're talking about, it would take you around about 14 days, 2 weeks. Even with the team technology of 200 cores, it still takes about 4 days to do that two-car simulation. It's nowhere near, absolutely nowhere near the agility that we need in order to develop a new Formula One, a better Formula One, okay? Partnering with AWS and their cloud HPC services, EC2, the first iteration for a two-car simulation, we got down to 11.5 hours. We're now at less than half. We're now at less than 8 hours. 8 hours to do a two-car simulation. So it's absolutely incredible what we've been able to do. It gave us the agility to be able to move forward. And I'm going to give you when we were putting this together, this talk together, I'm not American, I don't know whether any of you noticed, but some of the guys who were putting it together, they called these the face melting stats. And I think this really is face melting. This was an email that I received just some weeks ago about where we are now with what we call the Mike model, which is up there, okay? We had 7,300 cores solving 14 cases all at pretty much the same time. 2.7 billion cells within the CFD models to solve. And we did it all in less than 30 hours. It's absolutely incredible what we've been able to do. And what that's done is it's give you this behind me, the 2021 Challenger. This is what we hope is going to change Formula One. And we are hopeful. It's exactly what the fans are asking for. So what are the results? The results are this, okay? At 1 second behind, rather than losing the 30% of downforce, we're now losing 5% of downforce. All right. At half a second behind, 7%. It's huge. It means that the car's being pushed into the ground more. It means we can get this wheel-to-wheel action. Okay? It's exactly what we've been searching for. And we're really, really hopeful that it's going to make a better show. Okay? Two great companies, two great partnerships, okay, or a great partnership. Formula One, AWS, the DNA in problem solving. Thanks very much for having me. It's been an absolute pleasure.
We're seeing AWS put tremendous pressure on the limitations of on-premises infrastructure. HPC is awesome and has incredible implications for improving our everyday lives. Can AWS investments in infrastructure accelerate other workloads? I guess we'll have to stay tuned to find out. And now here's a guy that might have some answers for that. Peter?
Wow. That's cool, right? If that doesn't get you excited about HPC computing, literally nothing will. Literally nothing. So it's exciting to see an area like high-performance computing be reinvented. It's not just challenging to meet the technical requirements, but it takes a while to convince the practitioners that you can meet their needs and offer value that their existing solutions can't. We're well down the road with HPC. But let's look at a second area of computing where we get to work with practitioners from the start to build and invent the right infrastructure. And that area would be machine learning. Now, machine learning's been around for many years, but the last few years has really seen an explosion of new techniques and applications as applications have evolved rapidly and as advances in computing have enabled new approaches and previously impossible results. Machine learning is quickly becoming an integral part of every application. And AWS has been right in the middle of this from the very start. It's exciting because it gives us an opportunity to work directly with customers to understand their needs and invent infrastructure to make even more exciting things possible. A machine learning system is made up of two distinct and very different systems: training and inference. Training is where you create a machine learning model from your pre-labeled data. And inference is where you use that model to make predictions about new data. The optimal infrastructure for these two things are very different. So let's start by looking at training. There are a lot of different types of machine learning models out there, but they all work relatively the same. Generally, training a model involves building a mathematical model by computing on a carefully curated and labeled training data set. Machine learning models vary in complexity and size, but all training involves doing a large amount of floating point math and matrix operations. And over the last several years, deep learning models have grown significantly more complex. These models are highly interconnected, so solving one part of the model involves knowing what's going on in different parts of the model. A good machine learning data set is big, and they're getting bigger. Now we're talking about petabytes of data, or many, many hundreds of terabytes. And training involves doing multiple passes through your training data. So to actually solve your parameters, you have to get through that large data set several times. So the combination of bigger and more complicated models and ever-increasing training data set size is creating demand for high-performance computing infrastructure for machine learning training. If your problem's fortunate enough to respond well with a smaller model or a reasonable sized data set, you might train your model on a single powerful server with a set of tightly connected GPUs. For these sorts of training workloads, we have the P3 instance. A single EC2 P3 16XL instance has 8 NVIDIA Tesla V100 GPUs, and they're all interconnected with a proprietary fabric called NVLink. And so within the server, there's very high throughput and low latency between the GPUs. The P3s also have a 25 gigabit networking adapter, and this allows your training data to get to the instance very quickly. These are big instances, and they can do a lot of substantial model training. Let's look at some of the models that you can train with a P3 instance. Here you can see how the P3 performs on a few different models. These are common models, and they're used for a variety of different applications, and they're trained on well-known benchmark data sets. Now, you can see there's lots of models here that can be trained in a reasonable number of minutes or a short number of hours. And for these models, the P3 may be all you ever need. But let's look at that last entry, Mask RCNN. This is an object detection model that's very important to self-driving cars. It's moderately complex, and there is a lot of interest in improving it because it's so important to this machine learning space. So you want to improve it by doing tweaks to the model or changing your training data to get better results. But if you have to wait 3 hours every time you want to do this, it's going to get pretty frustrating pretty quickly. So how do we go faster? Well, we need to scale to more GPUs. So let's see what happens when we try to scale this Mask RCNN model over more P3s. Okay, this graph is showing you throughput of the Mask CNN cluster. Throughput is how many images you can process per second. So higher throughput is good. Higher throughput means you can train your Mask CNN model faster. If you can double your throughput, it will take half as long to train your model. Now, the first thing you can see about this graph is that adding more GPUs starts to help a little bit at the beginning. But we aren't getting nearly the speed up that we want. Doubling the size of the cluster maybe gives us 40% performance improvement. And worse yet, these gains deteriorate as the cluster gets bigger. Eventually, it just stops working at all. You can throw more GPUs and you get no additional speed up. So what do we do to make this cluster scale better? Well, let's look a little closer at how training workloads work. This picture probably looks familiar. Just like the HPC applications we looked at earlier tonight, these machine learning models are highly interconnected. So when you scale them over lots of servers, you need to periodically synchronize all the servers in your cluster. Now, while the synchronization is happening, the GPUs are not doing useful work. And this is what accounts for that waste in the scaling. So being able to accomplish the synchronization quickly keeps the cluster running efficiently. So to make our ML applications scale better, we need to use the same approach that we looked at to scale our HPC applications. And for that, we have the P3DN instance. The P3DN leverages all the investments I talked to you about earlier: the big, fast network fabric, the specialized Nitro controller, and EFA. And if you look really closely, you're going to see the same Nitro controller that I pointed out on the C5N earlier. Just like we discussed with HPC, we invested in integrating EFA with all the common tools that machine learning practitioners use, like TensorFlow, MXNet, and PyTorch. And we optimized the way those frameworks share their model parameters to take advantage of EFA. So as an ML practitioner, you don't have to know about all these details we've been talking about. All you need to know is you want to train your model faster. Let's look at training times on a P3DN. Okay, this is the same chart that we just looked at, showing our training throughput on the P3 cluster. It may look a little bit different, and that's because I changed the y-axis. And you're going to see why in a second. Let's look at how our throughput scales on a P3DN cluster of the same size. So if you look close, yeah, that's exciting. Yeah. If you look really closely, the P3DN, even at 8 GPUs, is a little bit faster. And this is because the P3DN actually has bigger, faster GPUs than the P3. But the really exciting thing is how you can scale the P3DNs and get consistent increases in performance. In fact, every time we double the GPUs in this cluster, we get about 85% performance improvement. So there's still a little bit of overhead to scaling, but not much. Okay, now that we know how to scale our workloads efficiently, let's look at a popular but even more demanding ML training workload. BERT is a popular machine learning model used for natural language understanding, or NLU. It's a complex model, and it has about 300 million model parameters, and it requires really big training sets to train well. To train BERT on a single P3DN instance with a large data set would take just over 9 days. Now, imagine having to wait a week to test a new idea or to try a new configuration. That would suck. So fortunately, you can use your P3DNs to scale up. Let's look at how well you can scale with P3DNs. But first, I want to look at P3DNs with off-the-shelf TensorFlow and TCP. Okay, so adding GPU helps here. You can get up to about 256 GPUs with off-the-shelf TensorFlow running on P3DNs. And if you do, you can complete your training run in about 14 hours. Well, that's pretty fast. Now you can do it once a day. But that's still not great. And if you add more GPUs after this, I didn't show it, but you pretty much hit a wall. You can throw additional GPUs at it, and it just costs more. It doesn't go any faster. So let's look what happens if we use EFA on those P3D instances. These yellow bars show those results. And because EFA makes the communication more efficient, we see we get better results at every cluster size. The same 256 GPU cluster now completes its training run in 8 hours. So just a little more than half the time of what it would do without EFA. But there's an even more exciting point with EFA, because we can keep scaling this cluster beyond the 256 GPUs. In fact, we can scale all the way up to 2,048 GPUs. And if we do that, we can complete our training run in just about an hour. 1 hour and 2 minutes, to be exact. Now, that's an incredible result. It's the difference between having to take a short lunch break between runs or a short vacation. One's going to be a little bit more productive. So we are really excited about the investments we've made in high-performance computing, and those same investments are helping us make amazing progress in training. But let's look at inference. It's very different. Inference is where you take the model that you train, and you use it to make predictions about new and unknown data. And in a production machine learning system, the vast majority of your computing is often used to do inference. And this kind of makes sense. Think of something like Alexa. The team might retrain their natural language understanding or their speech-to-text models once a week, twice a week. But every time a user utters a request, the system's doing inference. And it's actually doing multiple inferences. So inference can easily account for 90% of the cost of a production machine learning system. And with inference, latency matters a lot. When you're trying to use your model to figure something out, you often need to know very quickly. For example, in the case of Alexa, the faster you can interpret what is being said, the faster you can respond. And that's going to make your UI much more interesting to your customer. Or in the case of self-driving cars, the faster you can do an inference, the faster you can detect an object and avoid a collision. Also very important. So optimal infrastructure for inference has to help you do inference cost-effectively, but quickly. So if you want to do low latency and low cost, where do you start? Well, maybe you start by running it on the same server that you're running your application on. And for some models, this approach might work fine. But like we looked at earlier, training models are getting larger and more complex. And general purpose processors are not particularly good at the types of operations that are necessary to do inference. Much like training, inference, however, performs very well on GPUs. And the EC2 G4 server is the most cost-effective GPU instance for machine learning inference. The G4 has 8 NVIDIA T4 GPUs. Now, these are different, lower-cost GPUs than the ones we talked about on the P3. In fact, each of these GPUs only uses about 70 watts of power, compared to about 300 watts of power on those earlier GPUs. So you can see they all fit in the same server sled. We don't need a dedicated, they're just much smaller. Now, these GPUs were originally designed for graphics, but it turns out they perform really well on inference workloads, significantly better than CPUs. Let's have a look. Here we're comparing the inference time and throughput of the C5 instance with the G4. Both are using floating point numbers for maximum accuracy. Now, remember, the C5 instance is our optimized compute instance. This is the general purpose instance that we have that's for most demanding compute workloads. So the C5 is no slouch. And we're looking at a couple different models here. ResNet 50 is an image classification model. And BERT is that NLU model we just talked about. So what you can see is they're both complex models. They both put slightly different demands on their infrastructure. But not surprisingly, the G4 server performs significantly better on both in terms of latency and throughput. And it turns out I'm kind of underselling the G4 here, because these numbers are if you process each and every one of your inferences one at a time. And this can result in you actually underutilizing the resources on your GPU. So what you really want to do, if you can tolerate it, is batch up your inferences and make better use of the GPU. Let's look at how that works. Here we can see how latency and throughput vary as we start batching requests. Now you look at the yellow line, that's the general purpose CPU. And the first thing you're seeing on the C5 is batching doesn't help much at all. Latency goes way up, but you don't get much more throughput. And that's because the CPU is pretty much tapped out, just handling one inference at a time. It's not underutilized at all. The GPU, on the other hand, is much different. Initially, when we start to batch larger numbers of requests, we see a small increase in latency, but a dramatic increase in throughput. And as the batch size increases, throughput gains start to diminish a little, and latency starts to creep up. And at some point, this curve has a knee. And at that point, you're pretty much utilizing your GPU fully. And additional batching is just going to result in additional latency. Okay, So batching on a GPU is a great way to have low inference latency and low inference cost. The G4 is an excellent instance for inference. But last year at reInvent, we announced that we were working on a specialized AWS processor for machine learning inference. We call this processor Inferentia. Now, you're going to hear a lot about Inferentia this week. But tonight, I want to show you one of the ways we're innovating on Inferentia, the chip, to make inference throughput scale even better. Let's start by look at what happens on a GPU when you run an inference. OK, this is my pretty picture of a GPU. What you see here is a representation of one of the GPUs in a G4 instance. The GPU has a ton of specialized computing capacity that allows it to do floating point math and matrix operations very efficiently. But to do the work, the model has to be loaded into the GPU's local cache. And the cache is fairly small. So to handle the larger machine learning models we've been looking at, you need local memory. And you can see that local memory pictured at the bottom. Our GPUs have about 16 gigabytes of local memory. Every time a new inference arrives, all that memory needs to be sequentially loaded into the GPU. And this loading takes time. It's not a lot of time, but while this loading is happening, the GPU isn't being utilized efficiently. So we talked about batching, and batching can help you here. So here I'm illustrating batching. And when you have batching, you can actually drive the utilization of your GPU up, but you still need to cycle through that memory. And so you're still wasting time on the GPU. So with Inferentia, we looked at what we could do to make this more efficient. How could we achieve even better throughput by keeping our processor more utilized? Let's look at how that works. So similar to the GPU we just looked at, each Inferentia chip has a bunch of specialized computing capacity to do floating point math and matrix operations. And each Inferentia chip has a local cache that it computes on. In the case of Inferentia, that cache is bigger. And that means that we can load more of the model into the memory of Inferentia. Inferentia also has access to local memory, but I didn't picture it here because in the mode I'm talking about operating in, we're not going to use it. Rather than sequentially loading all that memory into Inferentia, we can shard the model over several Inferentia chips. Each chip holds a single shard of the machine learning model. And now Inferentia has a specialized communication protocol which allows one Inferentia chip to compute the results on its part of the model and hand its results off to the next chip. And you can see that illustrated here. Now, the result of this is that no time is wasted cycling through the memory. All the time is spent doing inference. So, I mentioned you're going to hear a lot about Inferentia, and I won't bore you with any more tonight. But this week you will hear a lot. One of the things you're going to hear about, if you're interested, is our team from Alexis here, and they're going to tell you more about how they're using Inferentia to drive down the cost and time of their inference infrastructure. But now, I want to bring a very exciting AWS customer up on stage to tell you about how they're using machine learning in AWS to reinvent drug development. Please join me in welcoming Daphne Koller from Insitro.
At Insitro, our goal is to make people healthier. And we're trying to do that by making better drugs and making them faster and cheaper. One can look at drug development from two perspectives. There's the glass half full perspective, which is this one, which is that in the last 50 years, we've made a big dent in infectious diseases, in cancer, in autoimmune diseases, in genetically inherited diseases. Diseases that once were a life sentence or a life of pain are now something that we can possibly manage and sometimes even cure. So that's the glass half full. The glass half empty is this curve, which has come to be called Eroom's law. All of us are familiar with Moore's law, which is an exponential increase in productivity. This is an exponential decrease in productivity of pharmaceutical R&D consistently over the last 70 years, and the trend is only continuing. This is obviously unsustainable. Now, why is that? It's because the path to drug development is full of forks in the road, where at each fork there is one path that leads you in the good direction and 99 paths that are going to fail, because biology is really complicated. And each of those failed paths costs a lot of money and takes a lot of time, so that eventually, as we go through the drug development process, each approved drug ends up costing us, and ends up bearing on its back the cost of many, many, many failures. Fundamentally, if you think about this, this is a problem of prediction. If we could only make predictions better and not take all these broken paths in the road, then perhaps a drug would not cost $2.5 billion to make. So what is the problem that we care most about predicting? There's a number, but the one that's most important is, what will an intervention do when I administer it to a human? How do we make such a prediction without the ability to experiment in humans, which is both really challenging and fundamentally immoral in most cases? So the way in which we currently do that is by using a model system, oftentimes a mouse. So mice don't actually get most of the diseases that inflict humans. They don't get Alzheimer's disease. They don't get cardiovascular disease. They don't get schizophrenia. So we create these diseases in a small furry beast with tails and an ear, and we hope that by curing that fake disease, somehow we learn something about humans, and that's why most drugs fail. What we'd really like to do is we'd like to use humans as a model system for humans. So how do we do that, given that we can't actually do experiments in humans? Well, fortunately for us, Mother Nature has made each and every one of us an experiment. Each of our genomes is different in thousands and thousands of different genes. And that combination creates a different phenotype for each of us. So can we use Mother Nature's experiments as a way of telling us about the connection between genes and function? Fortunately, the cost of sequencing has been on a Moore's law curve over the last 20 years since the first human genome was sequenced. In fact, the number of human genome sequences is going twice as fast as Moore's law, so that by 2025, we might have somewhere between 100 million and 2 billion human genomes sequenced. Now, genomes on their own are only useful in so much as one can tie them to clinical traits. And fortunately, here also there's been a growth in various biobanks, like the UK Biobank with 500,000 people, all of us here in the United States with 1 million people, with many, many phenotypes that are being measured for each of the people participating in those studies. So now we can put those together and really tie the genetics to the phenotypes, which suggest the causal connection between gene and function. So indeed, over the last 10 or so years, since there's been a growth in the number of what's called genome-wide association studies, where different diseases have been tied to individual human traits, disease traits as well as non-disease traits across a multitude of diseases. And so you would think that we would be done, because we would now have an understanding of the causal basis of disease and what we can, and then use those genes that are disease-causing as targets. The problem is that these diseases are complex. There's many hundreds or even thousands of genes that are often tied to a particular disease. And how do you know which of them to go after, when in aggregate, each of them only has a small effect, at least at the population level? So this is a challenging problem. What we're doing at Insitro is we're using another type of data to supplement human genetics. And that is based on a new revolution that's come about, which is that of high-content biological data, which allows us to get much closer to the causal biology. So here we are leveraging an amazing bag of tools that smart people have been developing over the past decade or so. First of all, there's the ability to create disease-relevant biological systems by taking cells, skin cells, from patients and controls, reverting them to what's called pluripotent stem cell status. And then we can create from that, from the skin of any person, neurons from that person, or hepatocytes, or cardiomyocytes, or multiple different types of cells that really allow us to understand what the disease looks like in those cells compared to healthy people. We can furthermore perturb those cells using genome engineering techniques such as CRISPR to create even more disease-causing genes, or fewer. And then finally, we can phenotype those cells, measuring them in many, many different ways to understand what sick cells look like relative to healthy cells. And finally, by using automation and microfluidics, that allows us to do this at unprecedented scale, creating masses, mountains of data. So let me explain what that abstract concept looks like. This is just a beautiful case study of a region in chromosome 16 that, for whatever reason, is mutated in a number of individuals. And it turns out that when it's deleted in people, it causes autism with probability 75%. And when it's duplicated, it causes schizophrenia with probability 40%. But we don't know why, because there's 25 genes in the region. We don't know which of them is responsible or how it does that. So a couple years ago, they took samples, skin samples from these patients from both types, reverted them to stem cell status, differentiated them into neurons, and they looked at them under the microscope, and what you see is this. You see that in the autism patients, there's an excess of synapses, and in the schizophrenia patients and the duplication patients, there's a depletion of synapses. That is a phenotype to which we can now screen and see if there's interventions that revert that phenotype and bring the patient back to healthy, hopefully. So that's all great, but it gives us data that looks like this. Mountains, hundreds of terabytes of data that looks like this. People can sift through this and make sense of it. So that's where we begin to deploy machine learning. Now, Peter talked about machine learning in his presentation, and I think the progress here is just mind-blowing, even to me, who's been working in this space for over 20 years. Back in 2005, when I was working in computer vision, if you were to show this image to a computer and ask it, is there a bear in this image, it would say, I don't know. 2012, there was more data, better algorithms, and the label to this image would be probably something like wolf. Now, there's no wolf in this image, but it's a wolfy-looking bear, so, you know, maybe. 2014, only 2 years later, the actual label, a brown bear is swimming in the water. This is now a phrase. Now, the bear isn't actually in the water, but it's a pretty darn good label. 2017, 2 brown bears sitting on top of rocks. Today, computers can label images, even natural images, better than people, despite the fact that we're trained to perform this task from birth. So imagine what would happen if we were to take this and apply this to cellular images. So one important thing is that you get from machine learning is not only classifications, you get some insight into the similarity of the domain. So the machine learning takes these images in this case and puts them in what's called a low-dimensional manifold, in which the adjacency in the manifold corresponds to semantic similarity. So these two images of trucks, which are very different from each other, very distant in pixel space, are actually close to each other on the manifold. They have to be because the computer has to label them the same way. Other images in other classes, like cars and tractors, are not in the same class, but they have some features in common, so they will be in the same general area, whereas images of cats and dogs and turtles will be in a completely different part of the space. So now imagine that we were to do this with cells. This is what we call the cellular phenotypic manifold, in which we place these images of cells on a manifold using machine learning. And now you can start to identify clusters of patients that might present clinically in the same way, but molecularly look very distinct to each other. And furthermore, we can screen for interventions that revert the yellow sick cluster to the blue healthy cluster, basically looking for drugs that work at the cellular level and hopefully will then also work for clinical outcomes. So effectively, what we've done is to put this infrastructure in place, and that required a tremendous amount of effort. It required a biodata factory that produces biological data at unprecedented scale. We've produced 95 terabytes just in the last 6 months, and that's while we were still working out the kinks. That speed is only accelerating. We need the help of our friends at AWS to give us compute infrastructure that can handle these terabytes of data of images that are 20,000 by 80,000 big. And we need to then design machine learning algorithms that are able to do this kind of classification, to look at cells and figure out genetically what they look like. So this is part of our early results. It's just baby steps for now, but it's already performing much better than the state of the art in identifying these interventions. And importantly, while building this infrastructure was really complicated, so the first time we did this took 3 months, the second time took 2 days, and we're only accelerating that with the infrastructure now in place. So what we're building is what we call the Insitro human platform, and it's an integrated closed loop between biological data generation at unprecedented scale using robotics and microfluidics and all these tools like CRISPR and iPS cells and so on, together with cutting-edge machine learning. And it's not 2 separate things. It's a closed feedback loop where the machine learning helps design the experiment and continually learns from it and feeds that back to the biological experiment with an integrated team of biologists and machine learning people and engineers working hand in hand as a single team. Now, we think this is really important, not only in itself, but because we think it's part of the next wave of science. If you look back at the history of science, you can see that it proceeds in epochs, where at a certain period of time, one discipline makes a huge amount of progress in a relatively short time frame because of a new way of looking at things or a new invention. In the 1870s, that science was chemistry, where we moved away from alchemy and turning lead into gold to understanding the periodic table. In the early 1900s, that science was physics, where we understood the connection between matter and energy and between space and time. In the 1950s, that science was computing, where the power of silicon chips allowed us to perform computations that up until that point, only people had been able to do, or even not them. And then, in the 1990s, there was an interesting bifurcation. 2 disciplines suddenly took off. One is the discipline of data science or machine learning, which is related to computing but different because it also involves statistics and optimization. And the other discipline was what you might call quantitative biology, where tools like super resolution microscopes and sequencing and microarrays, which measure transcriptional profiles, all of a sudden allowed us to measure biology quantitatively and at scale. And those 2 disciplines basically proceeded in parallel without much interaction until now. I think the next epoch of science, the one that's coming up in the 2020s, is what you might call digital biology, where we have the opportunity to measure biology at unprecedented fidelity and scale, to use machine learning to interpret what we're seeing, and then to use that insight to then go back and re-engineer biology to do something that is different from what it would normally otherwise do. I think that discipline, digital biology, is going to transform multiple parts of the world that we live in and is going to really help us change human health. And we look forward to doing that. Thank you very much.
Well, you may not know this, but I'm an AWS machine learning customer too. PFF is our company, and it's a data analytics company that serves all 32 NFL teams, 70 college teams, most major networks, and thousands of individual customers around the world. We collect so much data, there's really no way we could analyze it all, and that is until we met with AWS and started talking about machine learning. Our productivity skyrocketed, and AWS also provides us with incredible scalability. There are times that we are on multiple AWS servers and times that we're on a fraction of one server. But with AWS, it doesn't matter. They scale up or scale down automatically. But one thing we haven't heard about is AWS infrastructure. Peter, how about filling us in on that?
All right. That was a very different customer, but very inspiring. It's so exciting to see how innovative, promising, and exciting that research is. I'm going to wrap up quickly tonight with something very different, a look at our global infrastructure. I want to zoom way out. The AWS cloud spans 22 geographic regions, and we've announced 4 additional regions in Italy, South Africa, Indonesia, and Spain. When you look at a map like this, it's easy to think about these as points on the map, and that's helpful when you're thinking about where you want to run your application or where you want to store your data. But when you see a map like this, it's easy to underestimate what a region really is. Each of these locations is not a data center, Not even close. Each of these regions is made up of multiple availability zones. An availability zone is a partition of our infrastructure which is totally isolated from other partitions. And this is really important. Every AWS region has at least 2 availability zones, and most have 3. Some providers talk about having a large number of regions, but when you look at the fine print and you look really closely, only a few of their regions actually have availability zones. And as a customer, this makes it really difficult to know where you can run your applications with the availability and durability that you can get from availability zones. Across our 22 regions, we have 69 availability zones. And we have another 13 availability zones that are being constructed as part of those new regions or to bring our current regions up to 3 availability zones. Let's look at the rest of our global infrastructure. We have 210 global points of presence. We use these to peer directly with networks all around the world to assure that your customers get the best possible latency to the AWS infrastructure. In addition to these points of presence, we have a network of 97 direct connect locations. These locations allow you to peer directly with your data center or your office directly to AWS's global infrastructure. And when you peer with the AWS directly, you peer with all of our regions, so you can access any region from your direct connect location. Now that I've talked about the way you can connect to our network, let's look at the actual network. This is a big network. It spans the world and includes several subsea cables. And the network has enough excess capacity that it can quickly fail over from any fiber cut. Our global monitoring detects fiber path failures and automatically reroutes traffic. Most of the time, your customers and your applications won't even know this is happening. And one really important point that I've not talked about before with respect to our global infrastructure is that all of the traffic, our traffic and our customers' traffic, is automatically encrypted before leaving any AWS facility. I was surprised to learn that some very large cloud providers don't provide this assurance. Instead, they talk about how they control their network spans. This is simply not sufficient. Unless you're going to secure hundreds of thousands of miles of fiber down to the inch, and you can't do that, you simply must encrypt. Okay, it's been a while since I've given an update here at Monday Night Live on our sustainability efforts. So I want to close tonight with investments we're making in a very important part of our infrastructure, our renewable energy infrastructure. Earlier this year, Amazon and Global Optimism, a purpose-driven enterprise focused on social and environmental change, co-founded the Climate Pledge. The pledge calls for signatories to be net zero carbon across their businesses by 2040, a decade ahead of the Paris Agreement's goal of 2050. The Climate Pledge represents Amazon's desire to be a leader in helping the world move forward to a sustainable future. By joining the Climate Pledge and agreeing to decarbonize on this faster timeline, those who sign on will play a critical role in stimulating the investments in the development of low-carbon products and services, which will be necessary for all companies to be net zero carbon. Yeah, that is exciting. Companies that sign the Climate Pledge make 3 key commitments. First, they agree to measure and report greenhouse gas emissions on a regular basis. Second, they commit to implement decarbonization strategies in line with the Paris Agreement, including efficiency improvements, renewable energy, and other carbon emission elimination strategies. Finally, they commit to offset any remaining emissions with additional, quantifiable, real, permanent, and socially beneficial carbon offsets and achieve net zero carbon by 2040. Now, the key word in that last statement is real. These offsets need to really remove carbon from our environment. This is something we're really passionate about and something we're also working hard on. So we also shared our timeline for meeting the Climate Pledge. Amazon will reach 80% renewable energy in our global footprint by 2024 and 100% renewable by 2030. Now, both of these milestones are inclusive of Amazon's overall energy usage. And our final goal is to achieve net zero carbon by 2040. Major investments in renewable energy are a critical step in addressing Amazon's carbon footprint globally. And we're going to look at our progress there in just a moment. But 100% renewable energy alone doesn't get you to zero net carbon. Amazon's diverse businesses, like all businesses, have carbon impact beyond the electricity we directly use. For example, fulfilling customers' orders requires us to use transportation like tankers and sometimes airplanes, which today are powered by petroleum. And building data centers and other infrastructure releases carbon through a number of vectors. So in order to achieve the ultimate goal of zero net carbon, we're developing ways to radically reduce or eliminate carbon emissions from these processes. And so we're innovating across transportation, construction, and operations. Doing these activities without producing greenhouse gases or radically restricting the amount of greenhouse emissions produced requires solving many unsolved problems. And as innovators and builders, we're excited about these challenges. And I'm excited to see how we can apply our innovative efforts across the company to find solutions to delight customers without producing greenhouse gas emissions. We're very excited about the climate pledge and the opportunities to be leaders in this space. But let's look at the infrastructure component of our renewable energy. Here's a map showing the Amazon utility-scale renewable energy projects that we announced and delivered previous to this year. You can see that these projects have a capacity of 946 megawatts and include 4 wind and 6 solar projects. These projects are all in North America, which made sense at the time because that's where most of our demand was. But over the last couple years, we've come to a couple of realizations. The first realization is that we needed to learn to deliver renewable energy across the world so we could deliver renewable power to our global infrastructure. There are some places like India, Japan, and France, to name a few, where developing renewable energy projects is unusually challenging due to local regulations, laws, or because the energy market is not fully developed. We're deeply engaged in these countries to help shape laws and regulations which will allow us to move more rapidly with our renewable energy investments. Second, we understand to get to our 100% renewable goal in the time we want, we need to find ways to execute these projects faster. Renewable energy projects are complex, they can have long permitting processes, and not all countries where we operate have frameworks that allow us to execute. So we took a goal to find a way to significantly increase our renewable projects, not just in the US, but across the world. Let me update you on our progress so far this year. Here's the renewable projects that we have announced so far in 2019. In total, we've announced another 5 wind projects and 3 solar projects to produce an estimated 562 megawatts of renewable energy. And one really significant thing about this set of projects is that it includes our first projects outside the US, with projects in Ireland, Scotland, and Sweden. The 2 Ireland wind projects are the first unsubsidized renewable energy projects in the country of Ireland. This is hugely important to that country's renewable energy goals. These Irish projects will add 114 megawatts of renewable energy and will avoid $125 million in subsidy costs to Irish consumers. And in the UK, our wind project is the largest corporate renewable project ever. But we're not even close to done. And tonight, I'm excited to announce another set of new projects. Tonight, we're announcing an additional 6 renewable energy projects, 5 solar farms, and 1 wind farm. These projects will provide 711 megawatts of renewable energy capacity. And I'm excited as part of this announcement, we have our first non-US, non-EU project in Australia. That's exciting. So when you add these new projects, this will bring our 2019 project total to just about 1.23 gigawatts of renewable energy. This represents significantly more than Amazon's incremental global power consumption this year, and significantly more new projects than we've ever delivered previous to this year. You should look forward to regular updates in the coming years as we continue to announce new projects on our way to hit our renewable energy goals. I'm hopeful we'll have an even bigger set of projects to talk to you about next year. We've covered a lot of infrastructure topics this evening. I hope you've enjoyed seeing how customers are taking advantage of these innovations to run really demanding workloads on machine learning and high-performance computing. Before we go, I have just one more announcement.
Thanks, Peter. And that wraps everything up for this evening. We hope you had fun. And don't forget, tomorrow morning, you're going to get to hear from AWS CEO Andy Jassy. So enjoy Vegas, but don't party too hard.